we want to measure things about curves. We want to get to know curves. And one way to get to know them is by measuring characteristics about it. So we want to measure the curvature, and that means how much it bends, the curve bends. So let's say you have a curve that goes up and then it goes to the right horizontally. So it goes from up to horizontal in this fashion versus a curve that starts up again and eventually it turns horizontal. So up, horizontal, up, horizontal. But of course, those two curves are very different. If you are riding a bicycle, for example, and you want to do this kind of curve, um, you might want to go slower because inertia is going to make you go straight. And if you take this curve instead, even though you start with going in one direction and going perpendicular to that direction eventually, this takes longer. Now, somebody could argue, well, wait a minute, isn't this a zoom in of that? And that is an excellent point to make. We're assuming that the distances are the same. So assuming that, let's say this segment is the same, there you go, um, then, then we can see that this bends faster, bends more sharply than this. We want to have a precise way of obtaining a measurement of how sharp a curve bends. Um, so that's how we need to define, um, or that is why we need to define curvature. We're going to use um, kappa. So kappa is a lowercase Greek letter, which is called, of course, kappa. It looks like a K, but it's technically a kappa, and kappa is going to measure the curvature. So the direction that a curve takes at any given point is given by r prime. So r prime is this vector, and so is this vector, that would be r prime. Same thing here. So the question is how fast r prime changes with respect to the length of the curve itself. And that is how we're going to measure um, the curvature. So this is going to be a first attempt to define curvature. By the way, what I'm going to write is wrong, but I want to show you why it would be wrong. So, and that's why it is, I'm calling this first attempt. So again, we want to measure how fast r prime changes with respect to the length of the curve. Because if it changes this much, 90 degrees, and it takes this long to change, then that is a small curvature. It curves slowly. But if it takes only this little bit of distance to go from this direction to 90-degree direction relative to this one, man, that is a big sharp change in direction. So the first attempt, which is wrong, but I want to show you, would be the derivative of r prime with respect to the length of the curve. And curves go in space in all different directions. They don't have to go from left to right. We don't know which direction, a curve may go up and down or whatever. So we want to use the magnitude for that. Not to mention that would be a vector. And so we want to measure this as a single value. Okay, this doesn't work. Does not work. And let me show you why not. The reason is because let's do this again. So we start with this vector, for instance, or this direction, and we want to end up with this direction. So what we want to do by finding the derivative is looking at those two and see how much change there is relative to how long it takes to go from here to here. So again, this distance is what we're measuring relative to, and then we're going to divide by this distance. But there's a complication with this formula. The complication is that this vector could be much longer or much shorter than this one, depending on how fast the graph is being drawn. Remember, when we parameterize curves, you can put in one of the first videos about parameterizing curves. Let me just give you a quick example. Let's say you have x equals t and y equals 2t and z equals 3t. Well, that gives us a curve. If we use instead x equals t squared, y equals 2t squared, z equals 3t squared. By the way, this is gotta be to make them pretty much or very similar. Let's say t is greater than 0 in both cases, or not less than 0. In those cases, those two are going to give us the same graph. It is going to be a straight line in both cases, a ray actually, in both cases. But the way this guy is going to be drawn is going to be such that the vectors, as we move along, are going to get longer. The tangent vectors are going to be longer. So even though we have the same curvature, the same drawing for those, the tangent vectors are going to be different because eventually this is going to go much faster than that. So we have an ambiguity. Yeah, this vector could be fixed, but then this vector could be longer or shorter. Actually, both of them could be shorter or longer. And so these distances, this one or this one, are not going to be ambiguous depending on the parameterization, and consequently, they're not going to measure what we really want to measure. There's going to be an ambiguity. So this is a first attempt, but it doesn't work. Okay, so what we have to do is introduce the unit tangent vector, which we're going to label as t of t. And it is going to be defined as r prime of t, and then we're going to divide by the magnitude of itself. So when you have a curve, any kind of a curve, there is r prime, and the r prime here could be way longer or shorter, who knows, depending on the parameterization. Let me attempt to draw the same kind of curve. Here, this, if we use t instead, t is going to be a 1 unit long. T will be this long. And t here will be exactly the same 1 unit long. 1 unit, 1 unit, that is t, that is t. Of course, taken at different points on the curve. So when we compare one with the other, there's no ambiguity. This distance will be consistent, no matter how fast or how slow the curve is going. So we're going to use t instead. Our first attempt to figure out, to measure how fast something changes, was using the r prime rather, but r prime could be long or shorter. The direction is correct in any of those cases, but the vector itself could be longer or shorter depending on how fast the graph goes. This, by dividing by the length of the vector, we have pure direction. This is what I would call pure direction, because we have a unital length. So we don't have to worry about the length of the tangent vector. So we defined curvature, that's a k, no, a kappa rather, as the derivative of t with respect to the length. And again, we put absolute value in it. So when you have r, if you start with an r, curve r, you have to find the derivative. Then you have to find the magnitude. You have to divide. Well, actually, let's do this a little differently. This turns out to be by the chain rule equal to derivative of t, because the variable is little t. We could reparameterize this t with respect to s. We have done that in previous videos, but we did parameterize r. We did not parameterize t. That would make it. It is possible, but that would make it quite lengthy, unnecessarily more difficult than it has to be. So instead, we want to preserve the t instead of changing into an s. That doesn't take too much because we have the chain rule. So we can find the derivative of t with respect to little t, find the derivative of s with respect to little t, yep, and that will be the curvature. Yep. Let's start with an example. Let's call this example 1 of this video. Okay, our friend r of t will be cosine of t, sine of t, and 1, rather t, over 2 pi. So this is the helix that we have been using before. It goes around, comes back, 1 unit off from, well, from this point, which is 1, 0, 0. It goes up 1 unit. And we want to find the curvature at any point. Okay. So first, so the formula for curvature is dt over ds dt. There we go. So first we have to find t. In order to find t, we have to find r prime and then divide by the magnitude. So let's think about that with comma, capital T equals r prime over the magnitude of r prime. All right, so let's start again with r. R is cosine t, sine t, t over 2 pi. The derivative will be negative sine t, cosine t, 1 over 2 pi. I'm just doing derivatives one by one. The magnitude of the derivative will be the square root of this negative sine t squared plus cosine t squared plus 1 over 2 pi squared. And that's going to be sine squared because the negative vanishes after we square. The cosine squared and sine squared plus cosine squared, everybody knows, is 1. 1 plus 1 over 4 pi squared. And we have done this kind of computation before, 4 pi squared over 4 pi squared. We can change the 1 into that, plus 1 over 4 pi squared. It is nice to see things that are familiar. So we got same denominator, 4 pi squared plus 1 over 4 pi squared. And then we can split this into 2 roots, square root of 4 pi squared plus 1 over 2 pi. Yep, that is the magnitude. So we need to take this vector, r prime, so r prime is this guy, and we need to divide by this magnitude. Now, when we are dividing by this magnitude, um, we want to multiply by the reciprocal. This is a fraction. So capital T will be the reciprocal of this because we're dividing by this quantity, 2 pi, over the square root of 4 pi squared plus 1 times the vector. This is a scalar. This number is positive because pi is positive. So um, negative cosine, I'm sorry, negative sine of t. Here it is, cosine of t, and 1 over 2 pi. This quantity may, or may, the numbers here may be positive or negative. Um, let's put that to the side, and let's figure out. We're not going to take the absolute value yet. Oh, by the way, this is t. In order to find the curvature, we need to find the derivative of t with respect to little t. This is the unit tangent vector. By the way, that is, perhaps I did not mention what this is called. This is called the unit tangent vector. Okay, so we're gonna take the derivative of the unit tangent vector with respect to little t. Okay, that's next. So dt d little t is constant. Keep the constant. That is multiplying square root 4 pi squared plus 1. The derivative of sine is cosine, but we have a negative, negative cosine t. The derivative of cosine is negative sine. The derivative of a constant is 0. That's a 0. There. All right, so we have done some of this formula. We figured this out. And notice how much work we have to do. We have to find r prime, magnitude of r prime, then t, derivative of t. And this is a fairly simple function. Things get quite complicated. The computations are lengthy many times. The next thing to do is to figure out ds dt. So what about ds dt? Let me start out by reminding ourselves what s is. As a function of t, it is the integral from, well, some starting point, let's say a, to t of square root dx dt quantity squared plus dy dt quantity squared plus dz dt quantity squared. You just realized I made a mistake. Let me fix it very quickly. We may not have the same variable here as in the limit. So we're going to change this into a u. We're assuming that initially we have a variable u instead. There we go. Okay. But notice that this a to t is the same thing as the magnitude of a vector, the vector whose components are dx du, comma, dy du, comma, dz du, magnitude with respect to u. Yep. And this vector turns out to be precisely the derivative of r of u with respect to u. So a to t derivative of r of u with respect to u. Yeah. Du. Let me simplify this. This is the same thing as a t r prime du. Okay, well, s is equal to the integral of r prime. If we want to find the derivative of s with respect to t, t is the upper limit of this integral, then by the fundamental, well, there's two portions or two parts of the fundamental theorem of calculus. By one of the parts of the fundamental theorem of calculus, we know that we're just going to end up with r prime, the magnitude of r prime. Yep. So let's see. We want to find the curvature. The curvature is derivative of t with respect to little t, derivative of the unit tangent vector with respect to little t, over derivative of s with respect to t. Now, we just found out um, that this guy is the magnitude of r prime. And in our example, in our particular example we're working on, we know that dt, this quantity, the derivative of the unit tangent vector with respect to little t is this. So we need to divide by r prime. I'm going to try to squeeze that in here. Well, let's just write this down in a simplified form, dt, and now let's change this guy with what we had found earlier. So the curvature is equal to this vector, 2 pi over the square root of 4 pi squared plus 1, negative cosine of t, sine of t, negative 0. And then we're going to divide by a scalar, and this scalar will be r prime, the magnitude of r prime, which we found here. The magnitude of r prime is this guy, square root over 2 pi. So we're going to divide by the square root of 4 pi squared plus 1 over 2 pi. There we go. We need one more magnitude going here. This is a positive scalar, so this can exit the magnitude. What is the magnitude of this vector? Cosine squared, sine squared. We lose the negatives after we square, and 0. So cosine squared plus sine squared, we know that is going to be 1. And we're going to take the square root of 1, which is going to give us 1. So again, the magnitude of this vector will be 1. So we have this scalar divided by that scalar. And that is going to give us 4 pi squared, because remember, we multiply by the reciprocal when we are dividing by a fraction, over the square root of 4 pi squared plus 1. Yep. So that is the curvature of the helix. The helix that our friend, the helix that we've been working for a while. This is the exact answer. We will always ask for exact answers. If we compute this, if we punch this into a calculator, I took the time to do that. I ended up with about 0.975, 0.975. Um, we're going to talk about, we're going to come back to this in a moment. So what does curvature mean? Yeah. What does K mean? Uh, See, yes, we measure it. We're measuring correctly. We're measuring something. Can we think of it geometrically somehow? And the answer is absolutely yes. Let's say a curve goes straight across and suddenly changes directions versus another curve that goes and comes back but takes longer to do that. So both go and come back. We're assuming this is to scale, so it is not as if this was a zoom in of this. This is the same scale, same scale. Um, there is a circle that approximates this turn. There's a little circle that approximates that. It looks like we're looping around that little circle. There's a circle that approximates this turn. It's probably a little bigger than that. There we go. So this has a radius, whatever the radius are. I'm going to use, I guess, capital R because we're using little r for something else. So radius. So those are two different radius, even though I'm using the same letter. That is just the idea. So it turns out that the curvature is equal to 1 over the radius of the circle that approximates the curve at that one point. So again, curvature is exactly equal to 1 over the radius of circle that approximates curve. So the smaller the radius, since we're doing reciprocals, the bigger the curvature, the more it is going to turn, the faster it turns. The bigger the radius of the circle, because we're dividing, the smaller the curvature. So this is a small curvature compared to that one. Yeah. Just to give you an idea, for comparison purposes, the radius of Earth, I have to double check, but off the top of my head, I think it's somewhere in the neighborhood of 4,000 miles. So we're using miles as units. So the curvature on the surface of the Earth is about 1 over 4,000. So divide by 10, 100, 1,000. I think this is it. Let me double check with a calculator very quickly. 1 divided by 4,000. Yeah, 3 zeros and a 25. So that is the curvature, very, very tiny curvature of the, we're using miles as units, of Earth. So we know that Earth is round, of course, but it looks very flat because we have very, very tiny curvature. You cannot quite see how the Earth curves until you get to a plane or something very, very high. And then you can see the curvature of Earth. So this is a very, very, very tiny curvature. A curvature of 1 means that we have a circle of radius 1. A curvature of 200, boy, that would be very, very quick. Oh, so the reason why I wanted to to show you that is because I want to compare R of t and P of t. Remember our two examples? Let me remind you, P of t is the projection of R. R is cosine t, sine t, t over 2 pi versus P of t, which is the projection of this helix, this is a helix, onto the xy plane, so that we have cosine of x, rather t, um, sine of t, and 0. Yep. So let me show you both. So this is P. R is going to go, I have to do some auxiliary drawings here real quick. R is going to go all the way out to here, all the way to here, come back as it's still going up, and finish here by the time we get to 2 pi. So this is 1 unit, remember. This is R, P and R. Now, what is the curvature of P? Well, it is a circle of radius 1 unit. So the curve is approximated by itself. So the curvature is 1. The curvature here is about 0.975. Let me double check on my previous page. Yep. Remember, the curvature is exactly 4 pi squared over the square root of 4 pi squared plus 1. That is the exact value, and that's the answer, the kind of answer I'm going to ask you to please put on assignments. But I want to compare, so let's look at the numbers. This is 0.975, 975. So this curves harder, faster, more sharply than this. Not by much, but it does curve more sharply than that. And the question is why? If the projection gives us, if the projection of the helix gives us the circle, why is it curving less than this one? That's a good question. So why, if the circle is a projection of the helix, is the curvature of helix different than curvature of circle? And we can ask a second question, why is it less? Actually, by answering this question, we automatically answer the first question. And I think it is easier to answer why. By answering this second question, we can answer the first question. And I think it is easier to answer the second question. I'm going to let you think about that. Let's move on to 2D, curvatures in 2D. Oh, no. I missed something. Let me come back to curvature. So the curvature is defined as derivative of the unit tangent vector with respect to t over derivative of length with respect to t, and then take the magnitude of that vector. There's a shorter, I shouldn't say shorter, there's a different version for it. It turns out that this is equal to r prime cross product r double prime divided by the magnitude, after we take the magnitude of that cross product, r prime cubed. Oftentimes, this computation is easier than that, and it's definitely easier to remember than that. Yeah, I think the computation is just easier in many, many cases. In fact, we're going to repeat the same example. We're going to find the curvature of the helix again using this formula instead. So remember, and there's a reason for this. You're going to see how much faster it is to find curvature this way using this formula. Okay, so r equals cosine t, sine t, t over 2 pi, same helix we've been working on for a little while. R prime is negative sine t, cosine t, 1 over 2 pi. R double prime, negative cosine t, negative sine t, and 0. So here's the advantage. If this functions, at least one of the functions is relatively simple, especially if one of them is linear, after we find the second derivative, we're going to end up with a 0. And the cross product is simpler the more zeros there are. A lot of things are simpler, I suppose, if there's more zeros on it. Anyway, r prime crossed r double prime will be, remember how to do the cross product? We have a 0 here, so that's going to be 0 plus 1 over 2 pi sine of t. I believe this negative gets simplified with another negative from the multiplication, comma. And then we have a 0, 0 plus 1 over 2 pi cosine of t, but this time we preserve the negative because things change here, comma. And then this is interesting. Sine squared, they're negative, each one of them, but when we multiply them together, sine squared plus cosine squared. So we end up with a 1. Yep. The magnitude is the square root of this guy squared, so 1 over 4 pi squared sine squared t plus this negative vanishes after we square 1 over 4 pi squared cosine squared t plus 1. And we can factor out the 1 over 4 pi squared, and then we end up with sine squared plus cosine squared, which is going to be equal to 1. We still have this factor out, so we end up with the square root of 1 over 4 pi squared plus 1. And we've done this a few times. This is going to be the square root of 4 pi squared plus 1 over 2 pi. So this is a sort of a neat, clean computation. We haven't finished yet, though. Let's finish this up. R prime cubed. So there is R prime. The magnitude of R prime is sine squared, cosine squared. The negative cancels. So when we square sine squared plus cosine squared, that is 1 plus 1 over 4 pi squared. And again, we end up with 4 pi squared plus 1 over 2 pi. Okay, so the curvature will be this quantity, square root 4 pi squared plus 1 over 2 pi. divide that by this quantity, square root of 4 pi squared plus 1 over 2 pi, but the formula calls for cubing it. So of course, one of those factors will cancel off. We're going to end up with two of those factors remaining, and none up here after we simplify. Again, we have one of those, three of those, one of each simplifies, one on the top, one on the bottom. So we end up with 1 over 2 of those. We're dividing by this fraction, so that is the same thing as the reciprocals. And so the answer is 4 pi squared over 4 pi squared plus 1. I just noticed that in my previous sheet here, I did not simplify the root. This number is correct because I had computed this number earlier. But as I compare this answer, which should match this one, I realized that this, when we multiply by the reciprocal, the 2 pi and the 2 pi, yes, give us 4 pi squared. The root with the root should give us the quantity without the root. I apologize for that. Yep, yep. And this number is correct, though, after we don't take the square root. So those two numbers are exactly the same. And the computation here was more lengthy than here. So make sure you know how to find the curvature. And those are the formulas for the curvature. This is the one I think we should remember. How about curvature in 2D? Well, once you find something in 3D, oftentimes it is easy to go down to 2D. If you have a function f of x, just a regular old function, y equals f of x, just any function in general, we can embed this function into 3D. Technically, that is a two dimensional function, but we can embed it into a three-dimensional space. There is x and there is y by simply making z equal to 0. So we can define r of t as t, which represents x, f of t, and then 0. So there's the three components, x, y, z. So since we label this as x, we can think of x, f of x, and 0. All right, so what is the curvature? The curvature is r prime cross r double prime, r prime cubed. Well, let's figure this out. Let me rewrite r again. R is t, f. I'm going to omit the t. We know it's f of t, 0. R prime is 1, f prime still 0. R double prime, 0, f double prime still 0. But now we're going to cross r prime with r double prime following this formula. And we got a lot of zeros here. So this is going to give us 0, 0 when we do the cross product. And the only thing that is going to survive is f double prime, 1 times f double prime. The magnitude of this cross product is going to be 0 squared plus this guy squared after we take, and then after which we will take the square root. So let me write it down, 0 squared plus f double prime squared. So that's going to give us the magnitude, or just the absolute value of f double prime there. R prime, the magnitude of R prime, on the other hand, so we're using this guy to figure R prime. The magnitude of that will be the square root of 1 plus um, f prime squared plus 0. So, of course, we simplify this 0, and we end up with the square root of 1 plus f prime squared. So, in 2D, the curvature is found by the magnitude of the absolute value of the second derivative of the function over 1 plus f prime squared, that quantity to the 3/2. So this is the formula for the curvature in 2D. Let's do a second example. Let's say you have a regular parabola, y equals x squared. So that is the function. Let's quickly draw this. So I'm going to try to be somewhat accurate. 2, 2, 3, 4. So we have this curve, and we want to find, that's a regular parabola, and we want to find the curvature at different points of the parabola. All right, the curvature is, remember, the second derivative on top, 1 plus the first derivative on the bottom, square it to the 3/2. The reason why we have 3/2 is because back here, the magnitude of r prime was the square root, so that is the same thing as an exponent of a half. But then the formula for the curvature calls for cubing that. So we're going to cube, but then we're going to take the square root, so that's how we end up with 3/2 as the exponent. All right. So first derivative of x squared, you guys know it, 2x. That's the first derivative. So that goes here. So the curvature is 1 plus 2x quantity squared. That's the first derivative. And then we're going to do that to the 3/2. That's a parenthesis. Second derivative, well, it's 2, because the first derivative is 2x. The second derivative is 2. And we take the absolute value, but the absolute value of 2 is 2. So let's just simplify that exponent. So we have 2 over 1 plus 4x squared to the 3/2. So there is the generic formula for this for the curvature of this particular parabola. Okay, let's find the curvature at 0 when x is equal to 0. So this guy vanishes. That would be 0. 1 to the 3/2 is 1. So we end up with 2 over 1. What does that mean? That means that there's a circle that approximates the parabola at this point, and the circle has radius. It has to be the reciprocal of 2, a half. So there's a circle of radius half that approximates the parabola. If you draw this circle of radius half, the parabola and the circle are very much the same right here at 0, 0. What is the curvature when x is 1? Well, let's do this. This 2 is constant to anywhere on the parabola. 1 plus 1, 1 times 2 is 2, squared is 4, 3/2. That is 2 over 5 to the 3/2. Oftentimes, I rewrite this as 5 root 5, because 3/2 is 1.5. There's the 5 to the 1 and 5 to the 1/2. I think I figured that out earlier. 2 over 5 times square root of 5 is about 0.18. Oh, but actually, I want to know the radius. The radius, yeah, of the circle, so we are at 1, 1, 1. There is a circle that approximates the parabola at that point. And the radius of that circle will be the reciprocal of this curvature, 5 root 5 divided by 2, which is about 5.59. 5.59. So about 5.6. So there's a circle. Boy, that is going to be a big circle because if this is 1, that's 4. 5 would be about this much. So, whoa. So take this distance and put it here, perpendicular here. We got a circle of radius 5.59. So it's a big, huge circle. Kind of makes sense. Big circle here that approximates the parabola at this one point. This is interesting. The circle gets very, very big very quickly. The circle is tiny here, radius of 1/2, and then it gets way bigger. So a question just occurred to me. At what point on the parabola is the curvature going to be 1? So problem. At what point on the parabola y equals x squared, actually points, there's going to be 2 of them. I mean, here the radius of circle of curvature is 2, and as we move, that is the smallest it will be, and as we move to the right, it will increase. Rather, I said that wrong. The radius is 1/2, and as we move along, the radius of the circle will increase at least to 5 and change. So if we start with a radius of 1/2, and then by the time we get here, we have a radius of 5, almost 5.6, radius of 0.5 to radius of 5.6. There's somewhere in between where the radius of the circle that approximates the parabola is 1. So here's the problem. At what points on the parabola y equals x squared is the curvature equal to 1, question mark. And whenever I ask this, I'm assuming that we are looking for the exact, at what exact points on this parabola is the curvature 1, which means that the circle that approximates the parabola at those points will have a radius of 1. Yep, so here's the problem, and we're going to stop here.